We can often view complex polynomials as intricate mathematical structures that are built carefully from much more simple, fundamental building blocks. Formally, a polynomial is the sum of individual components, called monomials. In the highest degree term, we identify the coefficient and the exponent n. To be a polynomial of degree n, this coefficient must not equal 0. This leading non-zero term serves as the polynomial's anchor, defining its degree and providing the primary reference point for its behavior in an equation. Polynomials are often introduced as functions, mappings that take an input from the real number line and return a real number result. A polynomial with a maximum degree of 1 creates a straight line when graphed. Increasing the degree to 2 bends it into a parabola. While graphs help visualize outputs, understanding polynomial operations requires focusing on algebraic properties alone. We will use these properties to translate the manual process of polynomial arithmetic into a strict, highly programmable algorithm. Formalizing these steps into an algorithm allows computer systems to handle massive, multivariable equations with total precision. Consider the problem of adding a polynomial of degree 0, a simple constant, to a polynomial of degree 2. Our first expression, p of x, is x squared plus 4x plus 4. Our second is the constant 10. To structure this operation, we use a vertical grid organized by descending exponents. We place each term of our quadratic polynomial into its corresponding column in the top row. When we place the constant 10 in the second row, we find empty slots in the columns for higher degree terms. To maintain the structure for a computer, we use zero padding. We assign a coefficient of 0 to the missing x squared term. We do the same for the linear x term. Summing down the columns reveals our final degree 2 result. Because missing higher degree terms are treated as zeros, adding a polynomial of a lesser degree will not increase the maximum degree of the result. This grid logic holds even when two polynomials share no common exponents. Take a degree 4 polynomial, x to the 4th, and a degree 3 polynomial, x cubed plus 1. The maximum degree present across both expressions determines the total width of our matrix. We fill the first row with x to the 4th and use zeros to pad the empty columns below it. We fill the second row with our second expression, 0 padding the missing 4th degree slot and the internal terms. Summing the columns merges the disjoint terms into a single ordered sequence. This demonstrates that the maximum degree across the input polynomials defines the initial structural framework for the calculation. Our final challenge involves adding two polynomials of the same degree where multiple terms overlap. Here we have two degree 3 expressions aligned by their exponents. With the variables aligned, we can ignore the x terms and focus our arithmetic on the coefficients. In the x squared column, we simply add the coefficients. 2 plus 1 equals 3. We follow this same step for the remaining columns to reach the final result. Aligning exponents is the necessary first step that allows us to perform simple arithmetic on the coefficients to solve the equation. By generalizing these manual steps, we can define a universal rule for polynomial addition. This summation formula represents an algorithmic loop. It begins at index 0 and continues up to the maximum degree of the two polynomials. At each step k, the algorithm adds the coefficient a sub k to the coefficient b sub k. Zero padding ensures that even if a term is missing, the algorithm always has a numerical value to process at every step. This notation provides a rigorous, programmable method for adding any two polynomials. We have successfully turned the manual process of lining up terms into a structured computational loop. Does introducing subtraction require us to design a new algorithm? Mathematically, subtraction is essentially addition modified by a scalar. Using our clashing degree 3 polynomials again, we will subtract the bottom row from the top. Subtracting the second polynomial is equivalent to multiplying every term by -1. Distributing this -1 flips the signs of every coefficient. Multiplying by this constant scalar changes the numerical values of the coefficients, but the exponents remain exactly the same. Since a scalar has no variable component, it cannot change the degree of the polynomial. Because the exponents are unchanged, our existing framework is still valid. We can sum the columns exactly as we did before. We simply adjust the generalized algorithm by subtracting the coefficients at each step of the loop. By using zero padding to maintain alignment, we can use this exact algorithmic structure to process both addition and subtraction with completely consistent results.